strange way is that all the magnetic dipoles and the atoms in your material, below a certain temperature, if this material is ferromagnetic, they want to align and point in the same direction. And this generates a macroscopic magnetic field. That's what allows you to stick the magnets in the fridge. And so what happens here is what's the parameter, for example, and one thing you can do is you can start raising the temperature, and the thermal fluctuation, the effect of the heat, is to start disaligning some of these spins, right? Or magnetic, right? Let's call them spins. And what happens is that when you cross a certain critical temperature, there's just too much thermal fluctuations, right? And at some point, there's just too much rotation, and the material magnetizes. And so you can try this. I mean, this critical temperature is very high, like hundreds of Kelvin, maybe 1,000. But I was looking, and I found this material, this iron gadolinium, that's a free temperature, that's a transition temperature, is room temperature. And you can find it on Amazon. I went to buy, but there was no Amazon Prime, so I couldn't get it in time. But I believe that this should be a magnet, and if you hold it your hand long enough, it should magnetize, so it's not really good. And okay, so these are kind of conventional phases that we can experience, but there are an entire zoo of different phases of matter, and they can be bizarre and spooky, and this is what happens usually when quantum mechanics is involved. And to enter research, typically we have to lower the temperature when quantum mechanical effect becomes predominant. And one important example is superconductivity. So this was discovered 100 years ago, and in some material like mercury or metals, so essentially we know that for these materials we just need to provide a little peak of energy, and the electrons can leave the atoms and flow through the material, generating a current, right? And we all know that there is an intrinsic resistance, right? There are these tightly packed crystal atoms, there are thermal fluctuation again, so as we provide some energy to this material in the form of an electric field, some of this energy is lost. There is dissipation, there is heating. And as we decrease the temperature, this resistance decreases as well, and at some critical temperature, it's just dropped to zero. And what happens is that there's a phase transition from a metallic state to a superconducting state. And in the superconducting state, electrons flow through the material without losing energy. And this is a big deal, right? For like, it has an important impact in our everyday life, right? And so 100 years ago, there's a catch. And the catch is that the temperature when this happens is very, very low. It's 4 Kelvin, that's minus 270 Celsius. So we can realize this, but we just need to this very, very low temperature. So we need liquid helium typically to get to those temperatures, and higher it's very, very expensive. So we can scale this to a real, cool down power lines. Like 60 years later, around there, another type of superconductivity was discovered. This is referred to high temperature superconductivity. And the transition temperature when this type of material becomes superconductor is substantially higher. It's still low, we're talking about 150 Kelvin, but it's substantially higher than conventional superconductors. And one important point is that the microscopic mechanism behind this type of superconductivity is different from conventional superconductor. Those we understand, the theory was formulated in the 50s, and we understand the mechanism, but the highest temperature is like something 30 Kelvin, and this is a whole different type of physics. Okay? And this is I'd say like one of the biggest unsolved challenge of condensed matter, because if we can solve this problem, then we can find materials which can display superconductivity at room temperature. Okay? And one of the problems that prevent us to solve this problem is that the electrons in this material they possess very strong interactions. And like generally, when you're going to try to solve quantum mechanics for a large number of particles, you're going to find intrinsic complexity just by having a large number of particles interacting. And when the interactions are strong, things get much worse. Like when they are weakly interacting, you can circumvent this problem. When the interaction goes strong, you can find a way to overcome it. But that's one of the cases where we haven't found a way to solve this problem. And so at this point, I'd like to explain a little bit more in detail what I mean with this intrinsic complexity. And so what this refers to the many-body problem that we face in quantum many-body physics. And I think it's probably good to define a bit what a quantum state is, and I'll do it for the simplest possible case of one particle. And let's consider, let's stick to electrons, and let's strip away everything except the magnetic moment. So that's a very simplistic case, but that makes the point, right? So this object is quantum mechanical, and this property is quantized as an intrinsic property of particles, and electrons, they possess a spin, and the spin can be up, or it can be down. Now, the question is, how do we characterize the state of an electron, right? And when you enter the scale of atoms, particles, molecules, the microscopic scale, the physics is substantially different from what we're used to, right? From the physics that we experience here at the human scale. And one important property is that there is intrinsic randomness when you look at the matter and nature at this scale. So there is if we measure this property, if we take this electron and measure its spin, we're going to find that the spin is pointing up with some probability and it's pointing down with some other probability. And this is exactly intrinsic uncertainty. It's not all once. And I'll come back to that. And so the most general way to write down the state of an electron in this case is called wave function. And the wave function essentially is the most general form, and it tells essentially everything that you need to know about this type of measurement. Is expressed as two different coefficients, one for the state up and one for the state down, and these coefficients are related to the probability that you would found them out when you measure, right? So those are the square. And this intrinsic uncertainty resides in this principle which is called superposition. So the electron can be found in a superposition of these two states. And superposition itself is kind of like a hard concept. We don't have any counterparts in the classical world. So I'll try to make an example to make it clear. Hopefully it will be clear, or I will confuse you more. So let's consider equivalent superposition, right? That means that the electron is simultaneously in the state up and down with equal probability, 1/2. Okay. And what we need to think about this, because what does it mean to be in the same state simultaneously, right? So imagine this state as two waves, two different frequencies, and then you can think about the wave function as the sum of these two waves. So if you look at this, you can see that the two states are simultaneously present in the wave function with equal probability. Right? This is cartoonish, really definitely inaccurate, but the point is that you have these two states at the same time. Now we can't see this in practice. In practice, what we actually see is the black box. We can look at the wave function. So what you can do at this point point, you can ask the question, you can make a measurement, and when the state is in this superposition and you make a measurement, you can find one state, and this is what is, say, the collapse of the wave function without probability, and you can find the other state with the same probability. But let me make a thing clear. There is no ignorance, as I said. This is implicit randomness. Because I hear sometimes, if you only know the information about the state, then you can predict the outcome with certain probability. It's just misinformation. That's not what happens, right? There are no hidden variables to be found. This is what was the critique from Einstein. There are no hidden variables to be found. There is nobody keeping track of the state of the electron. It's not accurate. The state hasn't been it's just been in this counterintuitive superposition. And so this is one important point about quantum states. And another consequence of the superposition is that if you want to write the wave function for one electron, you're going to need two different numbers: the amplitudes for the state up and the amplitude for the state down, because you can find this in superposition. So if you want to store this state and somewhere on your computer, then maybe 1 year from now, you're going to need to insert two numbers, just in a text file, imagine something like that. And if you consider two electrons, what happens then? Well, two electrons that four possible states, like up, down, up, down, and down, down, right? But this is still a quantum mechanical object, so the wave function for the two electrons can be spread over all these four states simultaneously. So if you want to store this state, you're going to need to provide four numbers, or write down four numbers. What about period? Again, 8 possible states, 8 numbers, as you know where I'm going with this. If you keep increasing these n electrons to the n numbers, now that's a big number. And so essentially, you can imagine that if you want to store the wave function, you have this very long list of numbers that can be positive and negative. They can also be complex, but let's just keep it real. And so, just very big, but how big, right? Okay, I try to put things in perspective, always helps me somehow. For the electron, definitely not big, but if I want to store the wave function for 40 electrons, I'm going to need a 10 terabyte hard drive. Okay, well, you can get it. You can buy it. It's not super cheap, but it's fine. What about 56 electrons? Well, I'm going to need to buy one of these big containers, and I'm going to have to fill it with 88,000 hard drive. I guess we can probably have some more cost-efficient way, but what about 70 electrons? 70 electrons, I think this is the biggest ship container in the world. 21,000 containers, and again, when buying 90 electrons, you have to line up 1 million ships. That's as much space from the Earth to the Moon, full of containers, full of hard drives, full of numbers. 300 electrons is the number of atoms in the universe. 2 to the 10 to the 23 electrons is the more, but I don't know what is it, right? So, I mean, how are you doing, right? What's going on? This is just definitely exploding, infinite complexity, okay? I didn't tell you the worst part. I didn't tell you how to find the wave function, and just if I give it to you, that's how hard it is to store it somewhere, but you have to find it first. And to do that, you have to solve the Schrödinger equation. And what this essentially is, you have a microscopic model at H, we call it Hamiltonian, and this contains the properties of a single particle and how these particles interact, okay? That is the rule of the game, if you want. And we want to go from H to find a wave function that's the state of this many particle system satisfying the macroscopic model. And this is it's also an exponential problem, okay? So since the formation of quantum theory, this has been treated using calculus, and this works very well. So this works perfectly if you have an interaction, and works very well for weak interaction, but typically breaks down for a strongly correlated system. That's what we call it. And so what we do at CCQ and in our institute is that we apply a computational approach, right? So what we do is we try to encode this problem in some computer code, then we run this code in this very large supercomputer, maybe for 1 day, sometimes for a month. A colleague of mine in world will run a code for almost 2 years, then you're going to get a number, maybe more than one, and this is your answer, right? And so there are different ways to approach this, but there is a nice way to say, okay, well, I just do it first. I just take this microscopic model, I know how to solve it. This is just linear algebra, essentially. It's a pretty simple way that people think we know how to solve this equation. And if you try doing so, well, that's me trying to do so, and I get 16 electrons in this amount of time. If I get a bit more clever, I can get to 26. I think the record is 50, but not how this goes linearly, but then not the log scale. So this is exponential. So if you add 1 electron, then it becomes twice. It's like you can deal with it, right? So I'm just gonna flash now a few strategies that the community employed. That's the FT that we heard this morning. And a different strategy is using a compression. And essentially, the idea is that well, we have 300 electrons, and the wave function is as big as there's many atoms in the universe. I mean, but then you look at macroscopic physics, and it's not statistics. It doesn't seem that complex. So maybe there's some redundancy. Maybe quantum states you don't need that many number to treat them. And this is indeed the case in many situations. And you can compress this quantum state from this exponential mass to something which is polynomial, say. And this is what Bias is an expert in. And it's a fully quantum problem for him. There's other approaches, and one say, well, I have this quantum system, maybe 2 electrons moving, and I have this exponential scaling, and I can treat it. But then you think, well, if the system is classical, I know how to solve that. I have this powerful algorithm, but then when it becomes quantum mechanical, it's breakdown. So maybe I can find a way to transform this problem into something which is classical, and then solve that problem. And you can do this, and it sounds funny, but you add an extra dimension, and this quantum particle becomes like strings in this higher dimensional space, and you can solve this problem. Now, both the compression technique and mapping to classical systems, as well as the and the other, they have their strength and they have their limitation. For example, this IDC superconductivity is not the case where this technique can find a solution to this problem. One was just like find and say, well, naturally it's quantum mechanical, you use quantum mechanics to solve it. And so, before too, what you can do is that you try to solve some real quantum matter and you use a quantum computer to do so. And this is a simulation that I ran one of these small quantum computers, a simulation of magnetism, and this is the real solution, the one is not nothing else solved, they knew what the answer was. Then this is the solution that they got using this quantum computer with 3 different types of simulations. So it kind of works at the beginning, but then as it starts going bad. And this is because, as we were saying before, these devices are noisy. They don't have error correction. And we do error correction in classical computer and it works very well, but this is we're not yet there. So there are things you can do with these devices, but we can use it for large-scale quantum simulation just yet. And these are like 5 qubits. So it's not large scale. So, another paradigm, which is I'm more interested in, and this is more is what we say quantum emulation. That is, well, I have this real quantum material, I can solve it and have limited control on the type of measurement I can do in it. Maybe I can find some synthetic material that I can build in the lab, which has the same microscopic physics, right? But I can control, I have a high degree of control in it, so I can perform very specialized measurement, and I can tweak and I will these knobs and I can explore the genes where maybe they're not accessible in the real material. And the point is that by doing so it's like you're not solving the Schrodinger equation. Essentially, you're asking this to solve it for you. You're asking nature to solve the Schrodinger equation. You don't want to calculate psi, the wave function. You just let it solve itself. And then, well, then the problem doesn't just disappear, right? You have to find a way to extract it. So this means doing some measurement. And measurements means having data. And so the problem now it's just being rephrased. It doesn't disappear. Now we have to find a way to extract physics from data. So that's where all this machine learning and quantum manifest physics, they come together. And so let me tell you a little bit about that now. Physics from data, such a good thing, right? Well, I mean, people have been doing that for a long time, I'd say, like, yeah.
I just asked, so are you talking about like cold atoms?
Yes. Yeah, I will go give you in detail like a few slides, yeah. So data-driven physics, I'll forget the quantum for a moment. New thing, no, well, look at this guy, Tycho Brahe. There was like 1500, and he sat down and he looked at the stars for a long time, and he flew on this table. Position of the planets, position of the stars, okay? And these are called rule of fine tables, I believe. And this data led to the Kepler flows. So Kepler finished this table and was looking at it, and he found patterns in this state. And he came up with the Kepler flow by that. So that's impressive, right? 500 years ago. Other example, well, there was data that there was, let's say, part of the puzzle that led to the formation of quantum theory. And in particular, this gentleman, Rutherford, he proposed a model of atom which had a massive nucleus, and the electrons were orbiting around, okay? And this model had some problems, and one of the problems is that the electromagnetic radiation emitted by the atom, if you consider this model, should be continuous. There's these on the frequency that are the light emitted by the atoms. But when you do an experiment and you look at it, you find something like that, okay? A specific line, a specific frequency, so something's wrong, right? And so some people, Palmer, Lehman, and Rydberg also, I think, they found a way to predict the position of this line very, very accurately, doing something like some empiric formula. And this then suggested that indeed the structure of the atoms is something more like that, right? There are discrete energy levels, and this line, they correspond to transition of electrons from one level to another. So that's why they're discrete and they can only assume certain values. So let's fast forward to today. Okay, so this is something like this highly controlled experiment. I thought it was some kind of storage at first. I couldn't believe it, but then now this is the real deal. And I was at the time in Munich where most of these experiments were done, and I visited these labs, and I was amazed by what we could do, what we could achieve. And what they could do, they could cool down clouds of atoms and achieve essentially single atom control. So you can see here, these are atoms, like laser cool atoms. Okay, and those are very sophisticated experiments. And well, you can do more than that. You can actually draw things. So these are single atoms, believe it or not. And I could not at first say, wow, this is impressive. They can actually not only measure but control the single atom. And this, this provides very, very exciting possibility because you control quantum mechanics at its core, right? And so this is the data that I'm referring to, right? This is the quantum data. And clearly here there is nothing very deep going on. Here people, they just arrange this atom in some periodic structure. But then you could say, well, I can engineer this synthetic quantum method in this lab, which maybe emulates some other material I'm interested, or maybe just for the sake of exploring. And then I can make these very fine measurements, and this measurement will give me an insight on the physics side. If I'm looking for a wave function, that's where I'm going to find it. And so it's not going to be something like that. It's going to give me something like this. This is a simulation I ran the other day. You have spins, and they have single state and Kiel said. These are like high entangled state, and this thing fluctuates, as this is related to one of these topological phases of matter, which is like very exotic and interacting, strongly interacting. And what we can do really with Tycho Brahe, right? I can highball this and hopefully to find a wave function. But it's there, right? It's just hidden in some trivial way in this data. So that's what I mean when the problem is offloaded. But this I simulated because I knew how to, by imagining going into a lab, doing a measurement, getting something like this, and everything is encoded inside this data. And so, well, are we key to extract this information? That's the question, right? And that's where machine learning comes into play. And we heard in the previous talk a very good explanation of what's going on. And I'm gonna move to a couple of applications, if I think I can with time, of that's very recent works on how we can obtain some information that was previously not available using machine learning. Okay. So the first question is, can we validate reject theories from measurement data? Okay. And this is related to this high temperature superconductivity. So this is a bit the physics part, and just briefly describe it. And this is again, this is a platform that allows you to probe this type of physics. Now they can reach temperature like low enough to enter in the superconducting state, but they're getting closer. And so the idea is that, okay, we have the electrons in this double covalent material. Those are like these crystals, and they have this high temperature superconductivity. And then we want to do something which mimics this physics. So first we need the crystal, and these are called optical lattice, this crystal of light. So they shine two counter-propagating laser beams. There is an interference, a static pattern appears, and so essentially these are like patterns which mimics the potential that electrons feel inside crystals. Okay. So you don't want to use electrons, you want to use atoms. You have more control over them. And so what they do is that they load this mixture of lithium atoms, two different states for these atoms, one for spin up and spin down. They load these atoms into this lattice. So the idea is that they are trapped into two dimensions, and they should behave like electrons in this lattice. So as the same way as electrons, these atoms can move around, they have kinetic energy. And the same way as electrons, these atoms interact and charge. As charged particles, you have Coulomb interaction. But because electrons obey Pauli exclusion principle, the situation where two atoms with the same spin are in the same position, that's forbidden. And so that's why they use lithium atoms, because those are fermions. And fermions obey statistics. And so you do this, you see this kind of how the experiment works. You have these two type of atoms moving around, and then they can record images, and then you get something like that. So these are the atoms, right? This is just the grid, but this is the real picture of what's going on there. And this is the data that we want to use. Well, However, we still, and there are still like many theories that have been proposed to explain this phenomenon. And so imagine having two theories, okay? And so these two theories, don't mind what they are. There are two different theories. The goal is to explain the physics that they realize in this platform. And using these two theories, you can generate images, such as like this, right? And they're going to be different. This is just a cartoon picture, okay? And so we have two images. They belong to two different theories, and we have seen this before, right? That's the same thing of cats and dogs, okay? So the question is, can we build and train a neural network which is able to distinguish images from these two theories? And the images are just where the atoms are. That's very simple, okay? So we can use a neural network, and as before, we have the input layer, and these are going to be each, say, position in this grid, and say 1 if there is an atom, and 0 if there are no atoms. Then we have some more or less complicated network with some weights that we can adjust. And we're going to have two outputs. I mean, I'm going to have one because it's like a binary, but we're going to have two. It's like a bit more parameters here. I haven't done this. This is an experiment that's not been done in our group, but they used to. And essentially, this tells you what's the probability that some image here belongs to theory 1, and what's the probability that belongs to theory 2. Okay, and we know this probability that it sums to 1. So that's essentially the same strategy that we've seen before for the rectangles, and the strategy that we've seen for the natural images. Okay, and so ideally, what we want is that we feed an image of theory 1, we propagate the signals, and then we get some confidence. In 96%, then this image was produced using theory 1. And we can do the other way around, and we need the good confidence that this neuron lights up. Okay, and so this is done by training the network. I don't want to go into detail, but I just tell you once again the philosophy. And the point is, you want to find a set of ways which realize these two conditions that we showed before. And as you initialize this network and you propagate the signal, you're going to get something like that, something like half an amp or something which is wrong. And this is the right answer. So what you want to do, you want to take these weights and change them by using this calculus rule, so that at the next iteration, this number increases. Okay, and you do it again and again. Okay, and suppose that you succeed in this task, and then you've got a network that can reliably distinguish these two theories. Now what you can do is that you can feed experimental data, okay? And you can ask, well, what's the theory of this data? Okay, is it theory 1 or theory 2? Okay, that's what they did in this. That's very recent, a few months ago. And these are the results. These are one of these parameters that you choose in the space diagram. Essentially, when we are here, we have in average 1 atom per this breakpoint, and when we move away, we are essentially removing atoms. And here we cannot really understand what's going on, and as you move there, all this kind of simulation that we do breaks down. And this is the regime where the material becomes superconducting. It needs a lower temperature, so we are not crossing this boundary with the superconductivity, but that's the regime that we can solve. And so what the network does, it tells that in this low doping regime, the theory 1, the geometric strings, I don't mind this too much, explains the data, but and theory 2 in less. And this seems to cross, although there is not very much confidence there. Okay. And so why does this provide more information than the previous attempt? And the point is that there were done, you could do the same without a neural network. You could find some way to probe this. Like maybe you want to compare some measurements that you did, but then by doing so, you're introducing bias. You're saying, are this data from this theory and this theory according to my metric? And if we don't fully understand what's the correct metric to use, so we're going to get something which is unreliable. In fact, using the metrics, for example, correlation function, they weren't able to distinguish with good certainty which theory was explaining the data, but it seems to provide like at least a more confident answer, which is good. And okay, so you can build a classifier essentially to distinguish between two different theories, but then we can go a little bit further, right? And to say, well, can we use the neural network not to tell which theory the data resembles more, but to tell me directly the quantum state of the data? Okay, that's what I've been working on in particular. And in replacing the previous talk, what Yazan was saying is the one that I just showed you, supervised learning. You have data, the images of the atoms, and you have labels, the theories. I want to do unsupervised learning. I don't care about the table. I don't have the theories anymore. I just show the data, and I want to understand the structure of the data, which is the wave function. Okay, so that's what we had before. We had some experimental wave function which we don't know, but it's there. So that's what the state of the simulator is. And we do measurements, and then we feed to the network and tells which theory is more likely. Now we want to do something different. We want to have the same process here, feed to the data, and tell us the wave function. And the wave function can be related to the probability distribution on this input layer. So instead of saying what's the probability of this theory given an image, I want to know what's the probability of the image. And probably this connection is not obvious. There is much more to be said, but remember what I said in the previous slide, that the probability of measuring some state was the square of the coefficient of the wave function, right? And so this is what I want to measure here. If I have access to the distribution, then I get access to this coefficient. So I'm learning the wave function. So there is a catch, and that is I'm doing a square here. So we can it's a bit more involved, but we can distinguish even like positive and negative coefficients. It's just a bit more complicated. But say this is kind of the philosophy behind it. Right? We can relate this coefficient to the probability distribution of the data, but we can learn this probability distribution. That's what this neural network do using unsupervised learning. Okay, I'm going to show you an example. Now we are actively working with experiments. This is a work in progress, so I don't have like results to show for that, but I can show you something that we calculated last year, and this is all synthetic data, meaning that was us that generated the data in the first place using the computer, which is like a feedback. We generate the data, so we generate the wave function, we do the measurement, so we simulate the measurement process, then we construct the wave function, and we compare back.